Everyone, we're excited to present our work today. In our project, we aim to model the biomechanical behavior of a scarred uterus to predict and prevent uterine rupture, a life-threatening complication after a C-section. To achieve this, we developed a constitutive neural network that captures the anisotropic behavior of uterine tissue in a mouse model.
So for our assumptions, we're using a hyperelastic framework, and we're modeling the uterine tissue as transversely isotropic. Our data is derived from published uterine tissue uniaxial testing, and we digitized this data and then used it for our model. So for the equations, by modeling the uterine tissue as transversely isotropic, we can see how the deformation gradient and the fiber direction tensor play into their variant terms and the PL of stress. So displayed is our free energy function with 24 terms and 48 different weights. And then to optimize our model, we used L1 regularization, and we also checked the fit through the R-squared values.
And so for our model discovery architecture, we based R0 on a model from class, which was for uniaxial testing for isotropic incompressible materials. We added two new invariant terms, as well as an Ln activation function in order to model more complex mechanics. And these are the parameters we use for our testing. Now getting to the results. So for our control, across 3 different penalties, we saw that the I5 term dominates, and it had 5 activation functions. And for week 2, we again saw the I5 term dominates, and with a penalty of 0.5, there were 5 activated terms. And again, for week 3, again, we see that I5 dominates. However, this mechanics seems much simpler due to there only being 1 activated term for a penalty of 0.5, and the R-squared value being pretty consistent across the board.
So here are the plots for the control with different fiber angles. We see that R-squared increases as we increase the angle, and color changes, meaning different invariant terms activated. For alpha equals 45, only 5 terms are activated, and I5 dominates. In week 2, R-squared actually decreases slightly as we move away from alpha equals 0. With penalty 0.5, we still have 5 terms activated. As we increase the alpha, other terms dominate instead. As you can see, by 3 weeks, the difference in R-squared across angles is almost trivial, pointing towards a more mature, stable scar structure. The color change represents the change in dominating term from I5 to I3.
So overall, we saw that increasing the penalty reduced R-squared in the control group, which had no injury and no pregnancy, but had no effect after 2 to 3 weeks of scar healing, suggesting a loss of biomechanical component post-scar formation. And that higher fiber angles increase R-squared and activated terms in the control group, while after 2 to 3 weeks of healing, R-squared slightly decrease, indicating a shift towards isotropic variance. As far as our limitations, we had a limitation in our data collection because instead of using the raw experimental data, we extracted data points from the published graph, and we also only had access to uniaxial testing data, and our model may not capture the full complexity of the microstructure of tissues.